Hi, I'm Axel and welcome to our third episode of Instant AI with HemiStereo NX. Today, we'll use Python to access and work with the data of our sensor. In the last video, you saw the HemiStereo view of presenting the color image, the depth map and the point cloud. But if your application is good for previewing the results and fine-tuning the camera parameters, the data access is limited. To actually use the data in your own algorithms, they are available via API directly. Today, you'll learn how to use Python to access the API remotely. For this, we use a Jupyter Notebook server running on the sensor. As in the viewer application, we will access the same data outputs from the stereo backend. For this, we prepared the Jupyter Notebook as a ready-to-use environment on your sensor. But as our interface is based on the gRPC protocol, the API description can be easily compiled in any other programming language. Please refer to the gRPC documentation on how to do that for your preferred language and platform. Now, let's have a look at our setup. I already powered up the sensor and connected it via Ethernet to our company network, because I'll need internet access for the app installation later. We prepared an app containing the Jupyter Notebook as well as a fully featured Python environment. The app 3D-VL Jupyter is installed using the apt package manager. During installation, you'll be prompted for an access password and whether or not you want to create self-signed SSL certificates. Please remember the password and answer yes to the certificate question. Now the app has been installed. Let's check the status of the sensor and see what's going on. You can use the apps list command for that. As you can see, while the app is available, it is not yet running. For this, we need to start the app first. I would like to have it restarted automatically as well when I power cycle the sensor. So I enable it first. And now we can see the status of our available, enabled and running apps. The app is running now and we are done with the setup of the sensor. Let's close the terminal and fire up a web browser. Please enter the IP of your sensor, followed by port 8880 in the address bar of your browser. The self-signed certificate created during installation is used for encryption of the connection. Here we need to accept the security exception and continue. Also, please enter the password you set earlier. Now we have access to the Jupyter Notebook server. Let's just follow the folder structure and select the SDK Examples notebook for a start. Go to Samples, SDK Examples. The Jupyter kernel for this notebook is started automatically. First of all, let's run the whole notebook so we can see the output of each individual step during the in-depth discussion. In the menu, select Cell, Run All. This will take a few moments to complete. As you can see, the Python code has direct access to all of the sensor data. The Jupyter Notebook renders the results of each individual code cell directly into the browser, which is a nice feature for testing and prototyping purposes. Keep in mind though, all the image processing steps are done on the sensor. Using Python, we are only accessing the pre-calculated data via network interfaces. As mentioned earlier, the default stereo backend application running on your sensor is providing 3 types of data: the color image of the left camera, the calculated distance map, and finally the point cloud. Let's go quickly over the individual steps for retrieving the data. As with every Python script, we need to perform some setup steps first. In our example, we do not want to perform any analysis or further post-processing of the data. So this is pretty simple. All communication is done via the context object CTX, which is initialized with the target app name and the port of the gRPC gateway. Stereo in this case is the network name of the stereo backend application that provides the image data. You can use the context class also for connecting to other applications and also to other sensors. You would need to specify the correct IP address of the sensor and/or the application name here. As we've set up our connection now, we can try to access the data from the sensor. To see which data and properties are available in a specific application, the context object contains a getApplication method. This is useful for figuring out how a specific property or output is named and what type of data is to be expected. The data is acquired by the readTopic command and the topic name, which is just image here. This command returns a gRPC message object, which is the serialized image data plus some meta information. To work with the image, you need to transform it into a NumPy array first. To make things a little easier for you, we provide a helper function for that. It's called unpackMessage-to-NumPy. It results in a 3-dimensional NumPy array, which represents the RGB information of each individual pixel. Now, let's plot our image in the browser window. For this, we use the plotRGB command, which internally uses the IPyCanvas module. It renders the image into an HTML canvas object. You could also use matplotlib here or OpenCV, but I found the IPyCanvas module rendering the fastest. The distance is handled exactly the same as the RGB image, only this time the topic name changes to distance, obviously. The values of the intermediate NumPy array are representing the distance of the corresponding pixel in millimeters. The format NumPy to RGB call will change the data to produce a colorized image of the distance map and results in an RGB image again. Finally, we use the point cloud module for rendering the point cloud. Again, we need to access a different topic name here. The point cloud data itself contains only the Cartesian coordinates of each individual pixel, but not the camera image for colorization. To achieve the point cloud rendering, we need to combine the point cloud data with either the colorized distance map or the RGB camera image. This is done with the 2 commands shown here. As you can see, the point cloud rendering is actually interactive, so you can move around using the cursor of your mouse and have a look at it from different angles. Now, you have seen how easy it is to access the raw sensor data using the Python API. You have it readily available in NumPy objects, which can be used directly for further processing with, for example, OpenCV, PyTorch or TensorRT. Next time, we will dive deep into the AI inference using Jupyter. So long, stay tuned and goodbye.